So we had just now had a question about Rolle's theorem and why it doesn't apply for a cusp or a corner. The argument for a cusp would be the same as the argument for a corner. And remember what Rolle's theorem says. Rolle's theorem says if you have this situation where we don't have a corner or a cusp, so we have this curvy curve. If we have the case where we have 2 points that hit the same y value, well, in that case, we can find a tangent line parallel to the line through them. In particular, you can find a point where the derivative at that point is the same as the slope of that line. And in particular, you're going to get this pair of parallel lines. C, not A. And interpreting the middle point with the derivative says that we're going to be able to find a point where the derivative is 0. So why doesn't that apply for this case, where we can still find 2 points at the same y value? Well, at the top here, the derivative doesn't exist. And why does that derivative not exist? Well, remember, the derivative is a limit. So if the derivative is going to exist, then that limit is going to exist on each side, and it's going to be the same thing. On the left side, tangent lines in this case have a positive slope. On the right side of this point, tangent lines have a negative slope. So in the middle, this is, well, it's a constant positive slope, a constant negative slope. So the derivative here, that limit won't exist. So the derivative here doesn't exist. So that was the case with a corner. With a cusp, the same type of argument would apply, where you have positive slopes going to infinity, and you have negative slopes going to negative infinity, and the derivative there wouldn't exist. So in particular, you're not going to get this pair of parallel lines. Did that answer your question?
Yeah.
Okay. So this week we discussed the mean value theorem, and the mean value theorem is a generalization of this Rolle's theorem, where we take this diagram I had up here, you get a marker that works, and we tilt it on its side. And this marker is not working either. So the mean value theorem, so in this theorem we have zeros for the slopes, but the mean value theorem says we can tilt it on its side and we now have non-zero slopes. So given the assumptions, there is a point C inside A to B with the slope of the tangent line at C equal to the slope of the line through C. So slope of the tangent line at C, f prime of C, the slope of the line through those 2 points is the change in y divided by the change in x. It's a very important theorem. It gave us all of the results we needed for the following lecture on graphing. But the first 2 questions on this worksheet involve this observation. The first one directly, the second one a little less directly. There are 2 different ways you could do the second one. I'll do it in a certain way. But let's do the first one first. And I'm going to leave this on the board. Now, I find the mean value theorem equation kind of tough to memorize, but I find it much easier to remember the slope of those 2 lines. Now, this equation has F's and A's and B's and C's and primes all over the place. But now with the diagram, we just have the slopes of two lines, two parallel lines, and they have the same slope. So number one, for this function, show there is no value c with f prime of c equal to, what were our points, 1 and -1. So show that there's no value c that satisfies this equation. Well, let's find f prime. F prime of x is what? Well, power rule. X to the -1, derivative is -1 over x squared. So what we want to do is show that there is no c value where this value at c equals whatever that number is. What is this number? Well, f of 1 is 1 minus f of -1. F of -1 is -1. So we're trying to show that there's no value c where f prime of c equals +1. Well, if such a c existed, it must satisfy -1 over c squared equals 1. What happens when we solve this? Well, we get -1 equals c squared. No real, I guess maybe I should say real number. Now we're not doing complex number analysis. No real number c works. So if a c existed, its square must be -1, and that does not exist on the real number line. So that answers the first part directly. But since no c exists that satisfies this equation, it means the mean value theorem doesn't apply on -1 to 1. So why does the mean value theorem not apply on -1 to 1? Well, I'm gonna have to erase something. Well, what are the assumptions for the mean value theorem on -1 to 1? Well, we need a function which is continuous and differentiable. Well, we just take our function 1 over x. There's 1 over x. It's not continuous on -1 to 1. Is not continuous at 0. So the mean value theorem, abbreviated MVT, doesn't apply. You could also say it's not differentiable, but that is technically because it's not continuous. Any questions about that? Now, the number 2, I think there are 2 ways. I'll do the way that I was thinking of, and I'm going to try a second way after that to see if it works like that as well. So number 2, let f be a continuous function. We technically do not need that assumption, but I put it there for emphasis. If f of 1 equals 2 and f prime, slopes of tangent lines, is between 1 and 4 on the interval 1 to 6, then what are the maximum and minimum values f of 6 can be? Well, how are we going to do this? Well, we'll do it one way and then we'll try a second way. The mean value theorem tells us about the behavior of derivatives on intervals. Move 6 over there. Oh, this, I'm gonna move the camera a little. That's crooked. Sorry if that was distracting to anybody how crookedly I had the camera set up. That's a little better. So what do we have? We need bounds for f of 6. Well, we know f of 1 is 2. Yes. What else do we know? We know slopes of tangent lines on the interval 1 to 6 are at least 1 and at most 4. So this means whatever our function is, it's a continuous function, must satisfy that the slopes of tangent lines are larger than 1 or equal to 1. But at a minimum, the slopes of the tangent lines are going to be 1. So at a minimum, we'll say that's a slope 1. At a minimum, our function cannot go under that slope of 1. If it goes under this, you're going to find a point where the derivative is less than 1. But also, it's bounded above by 4. I'm going to have to draw that. That was poor planning. F of 1 is 2. We're looking for f of 6. F prime is between 4 and 1. Those were the numbers, right? Yes. So at a minimum, slopes of tangent lines are 1. So the function must be above, starts at this point, and must be above this line with slope 1. If it went below, let's just say it went below at some point, well, you're going to get points in here where the slopes of the tangent lines are less than 1. And that can't happen by this assumption on 1 to 6. And similarly, the slopes of tangent lines can't be larger than 4. So the function, whatever it is, must lie between or equal to, because we have equal to, those two dotted lines. We need what happens at 6. That's a lot of dotted lines. Maybe I should shade them in. Whatever. I already dotted them. What we really need to find are the bounds for f of 6. So we need to find those 2 points, those 2 y values. Well, how can we find these? This is length 5. This one starts at height 2. Slope of 1. What's the slope? It's like a rise over run. If that's going to be 1 on an interval of length 5, it must go up 5 units. Which tells us that that point 6, 7. Maybe I'll, what is it? It's 2 plus 5 times 1. Start at 2, interval of length 5, slope 1. Or you could, find an equation for the line. That's a little more detail than is necessary. And for the upper bound, well, we have an interval of length 5 again. Each horizontal unit causes the function to increase 4 units. So increasing 4 units across an interval of length 5 tells us it's going up 20. Starting at 2 tells us that that point is 6 and 22. And this is what it's 2 plus the length of the interval times the slope. So f of 6 is between 22 and 7. And that's the first way to do it. Implicitly using the mean value theorem to reach our conclusions about the interval 1 to 6. Any questions about that? The function must lie within this wedge or equal to that wedge. Must be here. starting at that point. So right here, we didn't directly use the mean value theorem equation. I believe we can use the mean value theorem equation to do this directly. So I'll call it way 2 for now. We're looking at the interval 1 to 6. So the slope of that secant line was what? F of 6 minus f of 1 over 5. And the mean value theorem says the derivative inside the interval 1 to 6 is equal to that 5 because it's 6 minus 1. But it also tells us f of 1 is 2. Well, we can use that and solve for f of 6. Solve for f of 6, multiply by 5, add 2. So f of 6 equals that. And this equation exists only because of the mean value theorem assumption. But since this is between, since the derivative is between 1 and 4, that tells you f of 6 is at least 5 times 1 plus 2, which is 7. And f of 6 is at most the largest. Yeah, but those are the same two equations that showed up before. So either way you would want to think of that is okay. Is my collar up? Yeah, okay, that's better. So any questions about number 2? I personally prefer the graph interpretation. And I think graphs are easier to see than equations. So any questions about 1 or 2? Okay. Number 3, we have 2 functions we want the graphs for. And here we're going to do that, well, using the methods we saw. And on the test, if you're asked one, you'll have to use the methods we saw. You can't just pick points. That's not calculus. What do we have? 2, -15, 9, -1. So we're going to sketch this graph, finding the intervals where the function's increasing, decreasing, concave up, concave down, then find a y-intercept, and then piece the graph together. So remember, our goal is going to be to piece together 1, 2, 3, no. Our goal is going to be to use calculus to piece together things like that. And we had about a half-hour lecture getting us to that point. But what do we need to do to find that? Well, we need the first and second derivatives. We need where there's 0, and we need to break up the number line at those points and then analyze. So this is 3a. I'm not going to fit everything on one board, so I'm going to do the calculus, and then I'll have to erase that and then do the graph. So we need our derivative. That's -15x. Sorry about that. Our derivative, -15 plus 18x minus 3x squared. We want where this equals 0. Just make sure I wrote that equation right. We want where this equals 0. Well, I'm going to pull a -3 out and write the x squared first because I see them easier like that. Pull a -3 off that, you're left with -6. You're left with 5. We want where that's 0. 5 and 1 make 5. 5 and 1 make 6. So we have x minus 5, x minus 1, and this equals 0 when x equals 1 or when x equals 5. And we're going to, with the first derivative, we're going to use those points to break up our number line, our real number line, into three intervals, and the function will always be increasing or it will always be decreasing on each of these three derivatives. And the value, the sign of the derivative on these intervals tells us which one. So what we need to do is evaluate the derivative at a point in each interval, and it'll always be positive or always be negative, because we already found where it crosses the x-axis. So f prime, a point over here, 0 is over here. Now you could use this equation, substitute. I always find the factored one easier to deal with in all cases except 0, because with that you just have to count signs. F prime is 0, it's negative 15, it's negative, or you could say it's negative times negative times negative, which is negative. In particular, it's negative. In this middle interval, we can pick a point here. I'll pick 3, I guess. F prime at 3 is negative times positive. So it's positive. F prime over here, pick a number there, let's say 6. 6 is after 5. F prime at 6 is negative, positive, positive. That's 1 negative. So our function is decreasing on that interval, increasing on that interval, and decreasing on this interval. And the conclusions about increasing and decreasing are for the original function. We're using derivative information to conclude or to reach conclusions about the original function. Any questions about where any of this came from?
Can you do f prime of 6 again?
Yes, f prime at 6. So when you put 6 in, you get a negative times a positive times a positive. So negative times positive gives us the negative. Any other questions about this so far? Okay, so the first derivative told us where the function was increasing or decreasing. The second derivative is going to tell us where it's concave up, where it's concave down. So let's find the second derivative. I'll use this one. So 18 minus 6x, where is this 0? Well, 8 times 3 is 16. 8 times 3 is 16. 6 times 3 is 18. 8 times 3 is not 16. So derivative is 18 minus 6x. That's 0 when x equals 3. So we'll split our real number line at 3. And now we'll do the same analysis, the same type of analysis with the second derivative. A number here on the left of 3, I'll choose 0. F second prime 0, 18 minus 0, which is positive. Second derivative at a number over there, so say 4 is 18 minus 24, which is negative. So the original function is concave up on the interval negative infinity to 3, open, and concave down on 3 to infinity, open. Any questions about this?
Do we have to like
Okay.
specify
Yeah.
whether or not it's concave up or concave down?
Can you ask that again? I said something in the beginning of your sentence. I didn't hear how you started that.
Do we have to like specify whether or not it's concave up or concave down? Or can we just like draw it based on like what we get?
there are, well, yeah, it's doing it the same way. What do you mean? Well, how would you? Do you mean if you don't, break up the number line and don't, and then just jump to the graph? Or do you mean make this observation and then do the graph? So
Wouldn't you need to do the observation to know that, like, to do the graph? Or like, is there a way to know before, like, you're graphing? Because I feel like I have to do the observation.
So if you, from here, didn't write concave up, concave down, you could piece together the graph. But you would need to make an observation about the sign of the second derivative and the sign of the first derivative. So if you, you would have to at some point observe the sign of the first derivative. So, it doesn't necessarily have to be a number line. In the graph, you could point it out. But there does have to be some observation about where the first derivative is positive and where the first derivative is negative. And it could be, you show the algebra and then you could make the observation in the graph, or it could be with a number line like this. I'm not sure if that answered your question. Did that answer your question?
Yeah, it did. Thank you.
Okay, if you, well, if you want, you can ask more in the office hour and show what you mean by that. I always write it out just because, in my mind, going from the sign of the derivative to the graph, I see it much better with the word decreasing than with the sign of the derivatives and with the word concave up, concave down. I just, in finding the pieces of the graph that we need, I like looking at the words rather than the signs of the derivatives. But here we're going to piece together the graph, and I guess I will have room for it here. Is that showing up on the board? Yeah. So our numbers are 1, 3, and 5.
Excuse me. I thought you said
Yes.
f prime of 0 was greater than 0. Or am I?
No, you're right.
Okay.
Thank you. That would have been, yes. Thank you for noticing that. It was 18 minus 6x. Thank you. You saved me making a mistake here. Saved me from making a mistake here, and then having to find a mistake. So we have these intervals. We have -3 to 1, then 1 to 3, 3 to 5, 5 to infinity. But to find the height of the function, so in terms of calculus, the calculus doesn't tell us if the curve is up here versus down here, but we can find that just by finding a point, and the easiest point to find is where x equals 0. So here x equals 0 when y equals 2. So that gives us our y-intercept. And now we're going to piece together pieces of the graph. -infinity to 1, decreasing, concave up. What is decreasing and concave up? Going through this point right here. This is decreasing, it's going down, and it's concave up. The caved in portion is pointing up. 1 to 3, it changes to increasing, but it's still concave up. increasing and concave up, looks like that. Cave portion is going up, function is going up. 3 to 5, it's still increasing, but it switches to going concave down. So it's going to do one of those. The caved in portion is down, still going up. And then on 5 to infinity, it decreases and changes to concave down. And this question does say to label them. I believe I do not say label with an ordered pair. Yeah, it just says label them. So a local maximum will be where it changes increasing to decreasing, or in the graph. It's a point that looks like that. A local minimum is where it changes decreasing to increasing. Or it's the point at the bottom like that. And an inflection point is where it changes. This is for that. Any questions about this? Technically not drawn to complete scale because that's below the y-axis, but that's fine. You know, we could move this y equals 0 line. This y equals 0 line is y equals -50 for this example. Any questions about this one? Okay, number B. We're going to do the same thing, but the function here is a little more complicated. We have 4 minus x squared all to the 5th. Okay, 4 minus x squared all to the 5th. Now, we're eventually going to need to set its derivative equal to 0, its second derivative equal to 0. And if you do expand this out into polynomial of degree 10, setting them equal to 0 is a real chore. But we have the chain rule, and that allows us to have a nice form for our two derivatives. So how do we do our first derivative? Well, function to the 5th. Derivative is 5 of them to the 4th. And then chain rule, multiply by the derivative of 4 minus x squared, which is -2x. I'm just going to combine the 5 and the -2x. So -10x, 4 minus x squared to the 4th. We want where this is 0. Technically, we also want where it's undefined, but you know, we're only going to deal with polynomials, so that won't show up. It equals 0 when, well, when 10x equals, well, -10x equals 0, which is when x equals 0, or when x squared equals 4. So positive or -2. And we're going to use this to break our number line, this case, this time into 3 pieces. But the derivative analysis is going to be the same. So f prime over here, let's choose -3. F prime here, -1. F prime of 1. F prime of 3. And we want the sign of the derivative. Now, before even doing any of this, notice we have 4 minus x squared to the 4th. That's always positive because it's raised to the 4th power. So in this analysis, we don't even have to think about 4 minus x squared to the 4th. We can just think of the -10x. And that helps a little, you know, it helps in terms of time saving because, you know, -10 times 3 is negative. -10 times 1 is negative. -10 times -1 is positive. -10 times -3 is positive. You know, so you could make that observation, or you know, you substitute -3, you get positive, sorry, -10 times negative, so positive times a negative to the 4th. So that's a positive. Either way, function is increasing over here. It's increasing over here. It's decreasing here. And it's decreasing there. Any questions about that? Okay. Now, second derivative, well, we have to take the derivative of this. And that, notice, is now a product. So we're going to need a product rule to take this derivative. So the two pieces I will take as, I want my handprint away from there, it's distracting. The two pieces I'll take as negative 10x and that quantity to the fourth. Derivative of negative 10x, negative 10. And then we need the derivative of this second piece, which is 4 of these to the third times negative 2x. So we have negative 2x times negative 10x. And maybe I'll write it like this. Minus 10x times 4 of them to the negative, or times negative 2x. So we have derivative of the first times the second plus the first times derivative of the second. Any questions about getting that derivative? So now we have some simplifying that'll help us. Not on this first piece yet. But we have a lot of numbers here. 10, 4, and 2 make what, 80? Negative, negative make positive. So we have positive 80 x squared times 4 minus x squared to the third. So the numbers make 80, x and x make x squared. And well, we could set this equals 0 and go from there. I'm going to factor first because these two terms have a lot in common. What do they have in common? Well, they have a 10. I guess I'm going to have to go to the top of the board eventually. Well, okay. What do they have in common? They both have a 10, but they also have 3 of these 4 minus x squareds. So I'll pull a 10 and 3 of those 4 minus x squareds off. And what are we left with? What are we left with here? Well, we're left with that negative, and we're left with another 4 minus x squared. You pull a 10 and 3 of these off of this second term, well, you're left with an 8. You're left with these two x's. I guess I might not have to go to the top yet. Any questions about that factoring here? So they have a 10 in common, and they have 3 4 minus x squareds in common. Peel them off this, you have a negative and another 4 minus x squared. Peel them off this, you have an 8 and an x squared. And now, how does this in here simplify? Well, negative 4, positive x squared, 8x squared gives us 9x squared and a negative 4. Is that showing up on camera? I'm going to rewrite that somewhere. I don't need the first derivative anymore. So the second derivative equals, I'm just going to rewrite that up here, 10 of these to the third times oh, times that, and that's definitely not showing up. Okay, any questions about finding the second derivative here? So right now, it is in a convenient factored form. We can set this equal to 0. You set that equal to 0. Well, you again get positive -2 from this term. But you also get positive -2/3 from that term. Set that equal to 0. What do you get? 9x² equals 4. X² equals 4/9. So you get x equals positive or -2/3. So now we're going to need to do our sign analysis with lots of intervals. Yeah, much easier with a bigger board. Well, I guess I'm going to do the second derivative down here. -2, -2/3, 2/3, and 2. We're looking at the sign of the second derivative. So we'll take a -3, take a -1, a 0 is there, a +1 is there, a +3 is there. We want the second derivative evaluated at all these. Well, I'm going to start at 0. At 0, we get positive, positive, negative. Negative because it's 0 - 4. Now, there are some, maybe, I don't want to say shortcut objects, but you could make symmetry arguments in finding these, but I'm just going to find all of them directly. Second derivative at 1, positive times positive times positive. Second derivative at 3, positive, negative, positive. That's not right. Positive, negative, positive gives 1 negative. And at -1, you're going to get the same as +1. At -3, the same as +3. Or you can substitute at -1, positive, positive, negative. Sorry. Positive, positive, positive. And at -3, positive, negative, positive. So you get negative. Well, now we have our concavity intervals. Concave down, this one looks like it just flips between them. And it does. Any questions about the second derivative? I probably could have written that in a more organized way. I'm just going to rewrite this first one so I can draw the graph up there. So now we need the graph. First, we're going to find the y-intercept. Let x equals 0. Gives you 4 to the 5th, which is what, 2 to the 10th. It's a positive number. We'll just say it's a positive number up there. It's a large positive number. 2 to the 10th. You could write it as 4 to the 5th if you want. What are all of our values? Well, we have -2 is relevant. negative 2/3 is relevant, 0 is going to be relevant, 2/3, and positive 2. We have a point up here and it's a relevant value. So I'm going to start at 0 to 2/3. 0 to 2/3. We're decreasing. We're concave down, decreasing, concave down. Looks like that. 2/3 to 2. We're decreasing still, but concave up. So it looks like that. 2 to infinity, decreasing, concave down. So it'll look like that. And here I'm just going to label these inflection points as we go. Inflection point there, inflection point there. Any questions about that half of the graph? Okay. So the other half, from negative 2/3 to 0, negative 2/3 to 0, concave down, but increasing. So from here to 0, concave down and increasing, looks like that. Negative 2 to 2/3, concave up and increasing. So it'll look like that, giving us this inflection point. And negative infinity to negative 2, concave down and increasing, giving us yet another inflection point. And up here, we have a local max inverter function. So any questions about this one? On your test next week, I already wrote the graphing question. So there is a graphing question. It's more like 3A than 3B. On your final, you may have one more complicated where you have more cases to consider, but the final is a 3-hour test. This is just a 1-hour test, so I would steer more toward the ones with fewer cases to consider.
Is there
But yes.
Is there like a local minimum on this or no? Because
This one has no local minimum. What does the directions say? Yeah, it says if they exist. So this one has no local minimum because it always goes off to negative infinity, but it also has none of those. It has no changes from in nowhere here does it go from decreasing to increasing. So yeah, there is no local minimum. Now, if there isn't one, then I guess in keeping with the directions, you don't have to label anything. But yeah, this one doesn't have one. If it says, is there a local minimum, then this one doesn't have one. This one also doesn't have an absolute minimum because it goes off to negative infinity. Any other questions about this one or anything on this worksheet? Okay, well, maybe I'll say something about the test. I've written about half of the test. So all of the topics in that list, I believe will show up in some form, the list I sent yesterday. L'Hopital's rule is not going to show up at all. It will show up on the final. The reason I'm taking it off this test is because 4B on the homework assignment, there were a bunch of mistakes. So, I didn't want to test that like a week after sending the feedback. So that'll, sometime after exam 2 and before the final, I'll talk a little more about that type of problem. But it will not show up on exam 2. It will definitely something like it show up on the final. Let's see, what else can I say about the test? There'll be a question. It's a 50-point test. There will be a question, probably 20, 25 points, find a few derivatives. We had implicit differentiation, we had logarithmic differentiation, chain rule. They'll all show up somewhere. Related rates, both approximations will probably show up, the linear approximation and the differentials. Extreme value theorem graphing, I would expect, a one kind of like 3A for the graphing, and for the extreme value theorem question. Did I write that one yet? I don't think I wrote that one yet. But I'm trying to remember the one that was what was on the worksheet. Well, I don't remember what was on the worksheet, but it will be the extreme value theorem. It will be set up similar to the last one from the extreme value theorem lecture, so you can keep that in mind. And the rest, definitely a good portion of this test will be on derivatives. So you can keep that in mind when you're studying. At least 20 points out of the 50 will be a derivative question, and the rest of the questions will also require the derivative in some form that'll show up. So do over the weekend practice the derivative computations. But for the last 15, 20 minutes of this, I'll leave this as an office hour for the next 15 minutes. Then at 12:15, I will send another link, a separate link for that office hour. So if you have any questions, you can stay here now and ask, or show up to the office hour. If not, I hope you enjoy your weekend.